We're going to take you a little bit further out in space with Victoria from NASA.
I'm wondering what you think about when you look at these pictures of a night sky, of the moon, or of the northern lights. I'm not only showing you pictures because it's the last talk of the day. We all survived. Congrats. It's been an awesome day. But also, when I look at these pictures, I'm wondering what these distant bodies in our solar system can tell us about our universe. So this is why I dedicated my career, my studies, my career at NASA Goddard Space Flight Center to study our solar system and to study space sciences, more particularly planetary science. So planetary science is our gateway from Earth, where we are, to study our universe, to understand our solar system, why are all these planets different, and also to understand if there is life elsewhere. Are we alone in the universe? But ultimately, it helps us understand the past and the future of our own planet. So we're not all space experts, but here is how I want to introduce space mission operations. So basically, we are on Earth. We have teams of scientists, of engineers in different labs at NASA, in other labs in the world. And these scientists, these experts, send homework to a spacecraft. In this case, a spacecraft on Mars. It seems very popular on Mars, so I'm very happy here. And so this spacecraft receives some homework and do the homework, and then send back the data back to Earth. And then the scientists look at the data, pre-process it, analyze it, and they decide what they want to do next. So it's an iterative process. And I think it's clear now with Ashley and Sam that communication in space is difficult. So even more when we want to go see other solar system missions. So we are on Earth, hopefully. And here I'm showing you sometimes the latency, the speed of light for one single photon to reach these other planets in our solar system. I'm working on a mission going to Mars, to Titan, to Venus, to ocean worlds in our solar system, and it takes time to communicate with them. And sometimes it's not even possible, because Earth is not in the line of sight of these planets. So sometimes we don't even hear of this spacecraft we sent. OK, so now we're experts. We understand that communication is hard in space, but we have other problems. In my research, one of the problems is that we can create instrument, build instrument in my lab and other labs that can generate so much more data that can be sent back to Earth. So we can have this amazing instrument, but we cannot send back the data to Earth. So we need to understand how to prioritize the data we want to send back. As one of my favorite colleagues say at work, we don't want to miss and to leave the Nobel Prize on another planet. So this is what my research is. We focus on science autonomy. Science autonomy is to give the ability to a space science instrument to analyze its own data on board in order to do some small tasks, like calibrate itself, like make mission-level decisions, and basically also learn how to prioritize the data we send back to Earth. So the long-term goal is this idea, where we collect data, we have this analysis on board the spacecraft, and then we ask this question, is it interesting? How you define interesting is a very tricky question, but if it's interesting, we send this data back to Earth in priority. If it's not that interesting, we tune the instrument. We know how to tune the instrument by itself on board to collect more interesting data. This seems great. For now, it's not possible. We have some challenges. Space missions rely on high heritage. Whatever worked in the past is what we do. So innovation is hard to put in place. It also costs money. We don't have the onboard computing power yet for space missions to have the onboard computer that can process these data. And the big question is trust. How do I tell my awesome team of scientists that I'm not going to leave the Nobel Prize on Titan? That's one of the questions. So for now, we focus on the short-term goal, where we develop this data science pipeline on Earth, in my lab at Goddard, in other lab, where we are going to study the data, in my case, mass spectra data, and we're going to work closely with the scientists to understand what they need, what they look at the data, what is in their brain when they look at the data, and we'll work closely with them to develop this data science team, this data science pipeline, and summarize the data, summarize the results we find, to then update the experiment we'll send to Mars. So I think it's clear that faraway planetary missions are hard. Space missions are difficult. And so one of the main challenges that we all talked about, Ashley, Sam, and myself, is communication. So we need some autonomy on board this mission. And we're at WIDS, Women in Data Science. We have a lot of tools for autonomy. One of them is data science, machine learning, software engineering. So I'm going to show you some tools that I'm using for autonomy development. There are very common tools. I'm sure most of you heard about these names of tools: EDA, exploratory data analysis, clustering algorithm, anomaly detection, neural networks, dimensionality reduction. And I'm going to show you how I'm using this tool in my research. I'm taking you to Mars. It's so popular, so right topic. So Mars, we have this mission coming there in 2028. It's named the ExoMars mission. It's a collaboration between ESA, the European Space Agency, and NASA, and it will land on Mars in 2030. On board this mission, we have an instrument that looks very fancy. It's my favorite. I'm completely biased. It's the one I'm working on. It's named MoMA. It's not the museum, but it's the Mars Organic Molecule Analyzer. Seems complicated. It's just a mass spectrometer that is going to seek for molecular signs of life, and it has a big focus on organics. So when we'll be on Mars in 2030, pretty soon, we'll drill in the surface of Mars, we'll collect a sample, we'll put this sample in the carousels, in the sample carousel, and then this sample will be studied by different instruments. So MoMA will be one of the first one. It will do a mass spectrometry experiment, whatever that means, and it will send back all the data back to Earth, to my scientists at Goddard and other partners in Europe, and they'll look at the data and they'll decide, this is very interesting. We should do another type of experiment. Maybe we just move on to the next sample. But they will have to make this decision in 24 hours. 24 hours or 48 hours. It's very time limited. So my work here is to help the scientists in their data analysis process. So I help them with the data science pipeline. And basically, we'll receive mass spectra data. This is the top image in this slide. And we have two stages. The first stage focuses on what we call the filtering stage, with dimensionality reduction and clustering algorithm. Here are some names of some of the algorithms we use. The talk before lunch was talking about UMAP. I also really like UMAP, so I'm glad it was introduced before. And here we want basically to filter the data. So we use dimensionality reduction algorithm and clustering. So this is unsupervised learning approach. And we have, hopefully my video works. Yes, it works. We developed these maps. As you can see, it's interactive, so that scientists can look at the data. Each color here represents a cluster. And we have access to the labels because we know what we tried in the lab, but we don't use the labels in this algorithm development. It's unsupervised. But if you looked at, when I was scrolling on the video, the pink cluster was only made of hematite compound. The green one, I think, was calcite. The other one was titanium oxide. So basically, our algorithm is able to cluster similar spectra together. And that will be helpful when we're on Mars, and the scientists really want to focus on what is new. So we'll have this data of new thing that we don't really know what it is, and we want the scientists to focus their 24 hours, 48 hours on this cluster. The final step is the matching stage, so where we develop our own neural networks to predict the chemical composition of the mass spectra data. Again, we have this customer also-like interface where we show the scientists this is the most similar spectrum from what we received, and this is our prediction, our neural network prediction of the chemical composition. It's chemical families. We can think of organics, inorganics. If there are chemists in the room, I'm sure you know a lot, way more than I do. And then we have chemical composition. It's hematite, it's calcite. We're lucky because we kind of know what we're looking for Mars. So I'm very excited about this research because it's a first step towards this science autonomy onboard mission, and I hope that we have future missions with that really on board and not just on Earth. I want to take the last 30 seconds of my talk to address you, the audience. We have a big role as future data scientists and as current data scientists. So we have a problem usually to solve, and we look at data, we look for the data, we sort the data, we arrange the data, we make nice plots. But it doesn't stop here. the data has a story to say, and you're the voice for this story to be said. So we all have a role, and we have to make this data talk, tell its story. In my case, it's to try to unveil the mystery of the universe. Thank you so much for your time.